Hello and good morning, everyone. Let's start the class now. So today we will introduce a function. So let me go to the first slide. And then after that, we will also introduce a new topic called graphs. Okay, so let me begin with the slides here. Okay, so what is a function? Okay, so here, let's see this example. Now we have 4 students here. So let's call him, this is Nobita, this is Shizuka, this is Takeshi, and this is Neo. Okay, so we have 4 students here, and then for some reason they have taken a mathematics class, and then these are the grades that in their first exam. So the first one gets an F, the third one also gets an F, the second student gets an A, and the last student gets a B. So in some sense, given a particular student that we have, we will know that the corresponding grade that he or she receives. So this is the concept of a function. So this is a function such that for every student that we consider, we will translate or we will link the student to one of the grades that he or she receives. So in general, a function is a relationship between two sets. So let's say we have two sets A and B. Both of them are non-empty. And then for a particular function, let's call it f. And then this function f, if we say that it is a function from A to B, then we mean that it is an assignment such that for every item of A, we will assign it to exactly one item of B. To describe this relationship, we use f colon A, a right arrow B, to represent this relationship, so that f is going to assign or map each item of A to a single item, one particular item of B. So in the previous example, the blue arrows, altogether, these 4 blue arrows altogether represents a function that maps or that assigns for each student a particular grade here. So this is the set big A set here, this is the set B here, and the function is the blue arrows. And we use the notation f of little a is equal to b to describe particularly for a particular little item A of big A, the resulting assignment will be equal to B in big B. So there is some name for it. B, we will call it the image of A, and A is one of the pre-image of B. Okay, so function is also called mapping or transformation. So mapping is really mean assignment, and transformation, you can easily see that we are somehow transforming a student here into a grade. So it is kind of a change, a transformation. Okay, so there are some more names to study here. So I hope you can all memorize it. So given a particular function f that maps items from A to items of B, the set A is called the domain. So domain means the home. Okay, so A is the domain, and then B is called the codomain. And then among all the items in the codomain, we can isolate those items that really have something that is mapped into. The corresponding subset of B will be called the range. So let's take a look at the first example here. In this example, the domain is the set of students, so it contains 4 students. The codomain is the set of grades, so there are 5 items A, B, C, D, F here. But if we want to talk about the range are exactly those items in the codomain such that there is someone who is mapped into. So the subset containing A, B, and F is called the range. Okay, so we have this understanding now. Domain here, codomain here, the range is a subset that just have A, B, and F. Okay, once we understand these concepts, we can describe three particularly important types of functions. The first one is called a one-to-one function, or an injective function, or simply an injection. So what is meant by a one-to-one function? A one-to-one function means that each item of A, when it is mapped to an item of B, such an item is not mapped by any other item from A. So it means like we are taking a flu shot. People are doing some injection to our skin. So the nurse will help us to, if they want to make multiple shots, so normally it is better to take shots at different locations. This is like this. So if a, so it means that when some of the item in the codomain is used already, it is not used by any other person else. Okay. So in such a case, it is called one-to-one. So it is not like 2-to-1, 3-to-1. It is not like there are many people, such that after doing the transformation or the mapping, it maps to the same place. So this is called a one-to-one function. So let's take a look at these two examples. The first one is the function f that maps from, that means the integer set, all kinds of integers, positive, negative, and 0, into integers, where the function fx maps x into x squared. Now, for here, we can see that it is not a one-to-one function. We just need to give an example. It is not one-to-one, it's done. For instance, f of 2 and then f of minus 2, they will both have the same value, 4. So in such a case, 2 and minus 2 will be mapped to the same location. It is 2-to-1, not 1-to-1. So it is not a one-to-one function. But then if we consider a different function, g, such that g maps, okay, the domain here is the set of natural numbers. So it starts from 1, 2, 3 up to infinity. It maps to integers with g of x is equal to x squared. Then in that case, you can see that it is a one-to-one function. So how do we show? Okay, we can show this by contradiction. So whenever, excuse me, we have two numbers that is mapped to the same location, then we will derive at a certain contradiction. So it implies that it is not true to be not one-to-one, so it must be one-to-one. Okay? Now the next type of function is called an onto function, or a surjective function, or a surjection. So surjective, it has the same starting part. The prefix part is like a surface of the Earth, surface of a sphere, surface of a cube, or whatever. So surface means something that is covering, right? Every part. So an onto function has the property that the range is exactly equal to the codomain. If it is the case, then every item of the codomain is being used. In such a case, it is a surjection. Let us take a look at this example. So the function f that maps integer into integer with fx is equal to 2x, is it a surjection? Now, this is not a surjection because the domain here, they are integers, right? So we will see that when x is an integer, 2x is also an integer. And in that case, 2 of x will be what? Will be an even number. So in such a case, then we will see that for some particular odd number, let's say 1, there is no particular x such that fx is equal to 1. So in such a case, something in the codomain is not used. So this is not a surjection. On the other hand, R, the function g that maps a real number into another real number with gx is equal to 2x, this time it is a surjection. And then we can show this to be true by claiming that for every number in the codomain, there is some particular number in the domain such that g of that number is equal to the desired number. So I will leave this for you as an exercise so that you can see how we can show something is a surjection. And finally, we can have a function called one-to-one onto, which means that it is at the same time one-to-one and also onto. This type of function, we also call them bijective function or a bijection. Bi means two direction. So two sides, they are injective. Okay, so it is called a bijection. So for instance, let's see this example, function f that maps an integer into another integer with fx is equal to 2x. So obviously, this is not a bijection because it is not an onto. On the other hand, g that maps a real number to another real number with gx is equal to 2x, then this is a bijection. Okay. Now, some checking. Okay, if you understand everything, then we will be able to figure out how to solve the following problems. These are counting problems. Suppose that we have two sets A and B. They are finite sets. The size of A is m, and the size of B is n. How many distinct injections are there from A to B? So for injection to happen, we must have n to be greater than or equal to m. Otherwise, by pigeonhole principle, there will be some item in the codomain being mapped by more than one item from the domain. So it is not going to be an injection. So for injection to occur, n has to be greater than or equal to m. And how many cases are there? So we can solve this by using what? We can solve this by using rule of product. So we just need to decide for each item of A, what is the corresponding item of big B that is going to be its image. So for the first item, let's say the first item in A, let's call it A1. So there are going to be n choice. And after that, for the second item, let's call it A2, there are going to be n minus 1 choice. So in that sense, the number of distinct injections will be equal to n to the power m, the following function. So n times n minus 1 times n minus 2. So altogether, there are m numbers multiplying together. So this is the number of injections. Now let's skip question 2 for now. Let's look at number of distinct bijections. Now for bijection to occur, we need what? We need the function to be both one-to-one and also onto. So in that sense, we must have n. This time, it has to be equal to m. Yeah, if n is too small, then it cannot be an injection. But if n is too large, then it cannot be a surjection. So altogether combined, we must have n is equal to m. And the number of distinct bijections is simply n factorial. Now to count the number of surjections, yeah, we can talk about this in the tutorial, but to find out what is the value of this one, we can rely on the principle of inclusion and exclusion. So I will leave this for you to think about, or check the OCW recordings for the answer if you want to know it earlier. And then in the remaining set of these slides, we have some more discussion of special functions like the floor function and the ceiling function. So these are for fun. So if you have time, yeah, take a look. Otherwise, we will talk about this after after we have finished the major topics in this course. So this is about the introduction of functions. This is the set of slides of lecture 10. We will also skip lecture 11 and lecture 12 and jump directly to lecture 13. If we have time left after we have covered everything, we will go back to lecture 11 and lecture 12. Lecture 13 is about another topic called graphs. Okay? So we will talk about what is meant by graph, and then there are some more new terms for you to memorize. We will also talk about some special simple graphs, and then in next week we will continue more discussion on this topic. So what is a graph? A graph consists of a non-empty set of vertices and also a set of edges where each edge connects two vertices. So it's better to have an example. For instance, this is an example. So this is an example of a graph with 4 vertices. Call them A, B, C, D. This is another example. This is an example of a graph with 4 vertices, and there is one edge joining the vertex 1 with itself, one edge joining 2 to 4, and then another edge also joining 2 to 4. So this is a graph with 4 vertices and 3 edges. And this is another graph. This graph has 4 vertices, and then there are going to be 6 edges. So to describe a graph, it is very easy. You just need to write down what is the set of vertices and what is the set of edges. Then in that sense, once these two are defined, then we can describe the graph without any ambiguity to any other people. Okay? Now, we have more terms. So notice that each edge connects 2 vertices. Sometimes they can be the same, like this case, and sometimes they may be different. Normally, the edges will be connecting 2 different vertices. Now, if each edge is connecting 2 different vertices, and then between 2 vertices there is at most 1 edge, then we call this graph a simple graph. So if you look at this one, this is a graph such that for each edge it is connecting 2 distinct vertices, and then between any 2 vertices there is at most 1 edge. So this is a simple graph. This is also a simple graph. There is no edge. So if we check whether the edge satisfies the condition that we need to follow, then it is automatically true. So in that sense, this is a graph. This is an empty graph without any edge, and then this is also a simple graph. Now for the one here, it is not simple for 2 reasons. First of all, it contains an edge that joins the same vertices together. So this is called a self-loop. So if a graph contains a self-loop, then it is not simple. Also, another reason here is between the vertices 2 and 4, there are more than 1 edge joining them together. So this scenario is called a multiple edges. So if a graph contains multiple edges, then, or multi-edges, for short, then this is also not a simple graph. So among the 3 graphs in these examples, then we will see that only the middle one is not a simple graph, but the other 2, they are both simple. Okay, another concept is called directed graph. So sometimes we want to specify the direction of an edge, because sometimes edge can be represented with some unequal relationship between the 2 vertices. For instance, vertices may be representing cities, and then the edges there maybe represent roads, and then the roads could be one way, or maybe the vertices could be representing animals, different types of animals, and then some animals will be the predator and some animals will be prey. Like the lion will take rabbit as prey. So in that sense, we may be using the edge as a relationship to tell us that which animal will eat which other animal. So in that case, we want to specify not just the relationship between two animals, but then we also want to specify which one is the predator and which one is the prey. So in that case, we will want to have direction on the edge. So the directed graph is defined like this. It is also easily or unambiguously defined when we specify what are the vertices and what are the edges. But this time, the set of edges will now be directed. It has direction. So this is an example. So this is a graph with 2 directed edge. This is a graph with 3 directed edge. And this is a graph with also, so here, this is the shorthand notation. So actually, this is the same as this one. We normally write the one in the middle for clarity, but then sometimes we may want to have shorthand notation so that this double arrow means there are 2 directed edges, one from Y to Z and the other is from Z to Y. Okay, let us test our understanding. So how many simple graphs with n vertices are there? If we know that, okay, so not how many, but let's say we have a simple graph with n vertices, and this time we want to count the maximum number of edges that this graph can have. So how many edges can there be? Remember, simple graph, there can't be self-loop, and there can't be multiple edges. Okay, so in that case, if GS is an undirected graph, then the total number of edges that it can have at most will be equal to n choose 2, because we can have at most one edge between any 2 vertices, so it is n choose 2. But if it is directed, then the edge joining from A to B will not be counted as the same as the edge joining from B to A. So in that sense, here, in this example here, this is also a simple graph. We don't have the same edge joining from the same vertex to the same vertex. Okay, although we have an edge here from Z to Y, another edge from Y to Z, these two are different edges. Unlike the directed case, unlike the undirected case, this edge and this edge, they are considered to be the same edge. But here, this directed edge and this directed edge, they are different. So in that sense, the number of edges in a simple directed graph with n vertices will be at most n times n minus 1. Okay? So for directed graph, so for undirected graph and directed graph, we have also some other terminology to study. So first of all, let E be an edge that connects the vertices U and V. So we will say that E is incident with U, or E is incident with V. So E is touching with U and touching with V. Okay? And then U and V will be called the endpoints of E. If U and V, so because U and V are connected by an edge directly, we will say that they are adjacent or they are neighbors. If it turns out that the edge is connecting the same endpoint together, then this edge is called a loop. We can define the degree of a vertex, so the notation is deg of V, to be the number of edges incident with V. But there is a special case. If it is a loop, so a loop will be like you have a loop, a self-loop. You have a vertex V, so we have an example here. We have a vertex C here, there's a loop here. Then we will count the degree here by, so normally degree counts the number of edge incident with the vertex. So basically, so for vertex A here, we count it is going to be 1, 2, and 3. This is the degree of this vertex. But for C, we will count this as 1, 2, 3, 4, 5. So it means that when it is a self loop, the number of edges incident with the vertex is counted as 2 rather than 1. Okay? So AC are neighbors, CE are neighbors, AB are neighbors, BD are neighbors, CD are neighbors. So these are the neighbors, and the degree here, A is 3, B is also 3, D is 2, C is 5. If no, C is 1, 2, 3, 4, 5. C is 5, E is 1, and F is 0. Now, there is a famous or important result called handshaking theorem. It's very simple result, but then it is also important. It says that for an undirected graph with m edges, the summation of the total degree of all the vertices, so this is the total degree of all the vertices, is always equal to 2 times m. So if you look at this example, this is 3, 3, 5, 2, 1, 0, 3, 3, 5, 2, 1, 0. It adds up to 14. And then how many edges are there? 1, 2, 3, 4, 5, 6, 7. There are 7 edges. So 14 is exactly the same as 2 times the number of edges, 7. The reason is very simple. We are using a combinatorial argument, because for each edge, it contributes 2, a value of 2 in the total degree. For this edge, it contributes 1 when we count the degree of E, and it contributes 1 when we count the degree of C. This edge contributes 1 to C, contributes 1 to D. The self loop here contributes 1 to C, and then another 1 to C. So in that case, we must have the total degree is equal to 2 times the number of edges. So we can borrow the same concept from the undirected graph to directed case. So let's say E is an edge, and this time it connects vertices from U to V. So there is a direction, okay? So this arrow is pointing from U to V. Then U is called the initial vertex, and then V is called the terminal vertex, okay? And then so when we talk about undirected case, we will say U and V are adjacent. Here, we want to specify also the direction. So we say U is adjacent to V. So it is like to means pointing to. So we will see that U is adjacent with V and the arrow is pointing to V. Okay. And this time V is adjacent from U. So the arrow is pointing from U. Okay. So from U to V. And then again, if U and V are the same vertex, so it means that the edge is a directed edge that connects a vertex back to itself, then it is also called a loop. Now for directed case, we will specify the degree more precisely. We will talk about the in degree and also the out degree. So the in degree is the number of edges pointing into V. So coming into V. So it is called in degree. And then the out degree is the number of edges pointing into V. And then out degree is the number of edges going out from U. Okay, so in that case, yeah, so minus means coming into, plus means going out. But don't worry, if you forget about whether you should use minus or plus, you can just write in DEG, in degree, or OUT-DEG, out degree. It is going to be as clear as you use the notation there. So for instance, if you look at this example, so if you focus on A, the in degree will be 1 because there's just one arrow pointing into A. The out degree will be 2. B has in degree 1, out degree 2. D has in degree 1, out degree 1. C, how about C? C has 1, 2, 3, 4. 4 in degree is equal to 4, and then 1 edge going out. So out degree 1. E is out degree 1, in degree 0. F is in and out both 0. So again, we have a handshaking theorem for the directed case. This time it is much easier. Yeah, we can see that the number total in degree and the total out degree, they are both equal to n. It's super simple, right? Because each edge contributes 1 for the in degree and 1 for the out degree. So it is this one. Actually, if you know this result first, then you can immediately obtain the result for the handshaking theorem for the undirected case. Yeah, we just have a directed graph first and then remove the direction, so we can have an undirected case after that. Okay, having said a lot of terminology, let me introduce some of the simple graphs that they are very commonly studied. So the first one is called a complete graph. The complete graph usually is denoted by, with n vertices, it is denoted by big K of n. Why we use K? Because K has the sound k, k, k to begin with, K, right? So it is the same as complete, because complete starts with k, 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 the sound k. So we use Kn to represent complete graph with n vertices. So it is an undirected graph with n vertices, with every pair of vertices connected by an edge. So all the graphs that we are talking about, they are all simple, okay? So K1 is just this one, K2 is this one, an edge, K3 is a triangle, K4 is something that we have seen already, K5 is we have 5 vertices, and then we join each pair of vertices with an edge. Okay, so this is called a complete graph. And then a cycle graph. Okay, a cycle graph is the vertices with the edge, they form a cycle. So in this case, this is a cycle graph with 3 vertices, a cycle graph with 4 vertices, and so on and so forth. We use C of n to represent a cycle graph with n vertices. So why we use C? Because cycle starts with C, okay? And then we have the wheel graph. Wheel graph is just a cycle graph with an extra vertex. So you start with a cycle graph Cn, and then add an extra vertex. We will form a wheel graph Wn. The extra vertex joins with every vertex on the original cycle graph. So it looks like, yeah, it looks like a wheel, the wheel on the bus, right? So this is W3. So notice that W3 has 4 vertices. So the 3 specifies the cycle. Okay, with the cycle of length 3, we add an extra one, W4, W5, and W6. And then there's the cube graph. Cube graph is denoted by Qn. So I think you can immediately understand why we want to use Q to represent the cube graph. Yeah, it's because Q and cube, they have nearly the same sound. So a cube graph, yeah, this is the formal definition, but then it is much easier to understand by example. So this an n cube or an n-dimensional cube usually. So this is a one-dimensional cube, so we don't see anything special. It is just a simple edge. It is something called the two-dimensional edge. So it is also not simple. It looks like a square. This is actually a C4. But then why we call it a cube graph is because of this one. This really looks like a cube in our daily life. This is a 3-dimensional cube. And how is a cube graph defined? Okay, so we begin with a 1-dimensional cube, which is just an edge. To get a 2-dimensional cube, we have 2 copies of the 1-dimensional cube. So we have an edge here, and then an edge here, 2 copies, and then we link the corresponding vertices of each copy together. So once we have this edge and this edge, we link it and link it. So we get a 2-dimensional cube. To get a 3-dimensional cube, it is also easy. We have 2 copies of the 2-dimensional cube. Let's say we have this square and this square. And after that, we link the corresponding vertices together by an edge. So this forms a 3-dimensional cube. And to get a 4-dimensional cube, we draw 2 of the 3-dimensional cube first. We draw a 3 cube here, we draw another 3 cube here, and after that, we join the corresponding vertices together by an edge. So in that case, we have a 4 cube. So an n-dimensional cube can be defined recursively, iteratively using this idea. So it is easy to see that the number of vertices in an n-dimensional cube is exactly 2 to the power n, and you can also count the number of edges, and also you can also count the maximum, no, not the maximum, so we can also see that to travel from one vertex to another vertex, it takes at most n steps to do so. At most. Sometimes it is faster, sometimes it is slower, but then it takes at most n steps. Yeah, although we have 2 to the power n vertices, exponential number of vertices, but then with this design, then the number of steps to go from one vertex to another is really short. It is like the log of the total number of vertices. So that's why n cube is really useful when we are designing networks that connect a lot of computers together. Okay, finally, this special graph that I want to talk about is called the bipartite graph. So bipartite, if we decompose this English word into to see what is the meaning, bi means two, partite means part. It means that the graph has two parts. What does that mean? It means that the vertices of the graph can be separated into two groups such that, so let's say one group is the white vertices and the other group is the black vertices, such that there is always no edge between vertices from the same group. So in other words, any edge that you see must be joining vertices from different groups. So this is an example of a bipartite graph. So this is, let's say, imagine this is the white vertices. These are the black vertices. So black do not join with black, white do not join with white, and all the edges are joining with different colored vertices. So this is also a bipartite. So we can see that we can think of these vertices as white and these two as black, and then this is going to be a bipartite graph. Now for this one, although it doesn't look like bipartite from the first glance, but then we can see that we can color this vertex, this vertex, this vertex as white, and this as black, so that all the edge that we can see, they are joining vertices from different color groups. Or, equivalently, we don't see any edge joining vertices from the same group. So this is also an example of a bipartite graph. Now this one is not a bipartite. No matter how we divide the vertices into two groups, we will see that there must be some edge joining vertices from the same group. So for instance, if we color this as black, this as white, then we don't know how to color this, right? And similarly, this is also a non-bipartite graph. So if you understand what is the meaning of a bipartite graph, you can challenge yourself to see which of these following graphs is a bipartite graph and which one is not. So I can tell you that one of them is a bipartite graph and one of them is not. Maybe it looks like it is a hard problem from the first glance again, but then it turns out that there is a very easy method to solve this. So I will leave this as our discussion next week. Okay, so that's all for what I want to introduce today. And then shortly after this lecture summary, I will send out the assignment 5 for the voluntary assignment 5 for you to try. Okay. Yeah, thank you very much. Okay, so that's all for today. Thanks all. And then we will resume our tutorial next Monday, and probably I will talk about how to count the number of suggestions. Okay, that's all for today. Thank you.